Today, the journey begins not on the Moon, but in the vast silence between Earth and its nearest companion, where Artemis II carries human beings farther than any crew has travelled in more than half a century, tracing a great arc around the Moon for all humanity. In this video, the mission unfolds from launch to lunar flyby to the long return home, revealing how Orion, NASA, and an international crew open the next chapter of deep space exploration. If this kind of calm space documentary is meaningful, please like the video, subscribe to the channel, and come along for the voyage. Far above Earth's weather and beyond the last thin trace of air, the space between Earth and the Moon opens as a wide and quiet region. It is not empty in any simple sense. It is shaped by distance, motion, gravity, light, radiation, dust, and time. Here the Artemis II mission finds its broadest setting. Before any task is reduced to a vehicle, a cabin, or a human routine, it belongs to this larger place, often called cislunar space. The term means the region between Earth and the Moon on the Earth side of the lunar orbit. The average distance to the Moon is about 384,000 kilometers, yet that measure is never exact. The Moon follows an oval path, so it sometimes moves closer and sometimes farther away. Even this gentle variation changes timing, speed, and geometry across the region. In this setting, nothing truly stands still. Earth rotates beneath its cloud layers and oceans, turning daylight into night and night into daylight. The Moon circles Earth in a regular rhythm. Both worlds also move around the Sun. Cislunar space is therefore not a fixed stage. It is a moving arrangement in which every body carries more than one motion at once. A craft crossing it does not travel through stillness. It enters a changing balance of directions and pulls. These pulls are mostly invisible, yet they define the shape of every path. What appears black and open is actually ordered by the steady action of gravity. Near Earth, gravity is strongest. The planet creates the main well of attraction in this region. Guiding satellites, debris, and spacecraft farther out. The Moon adds its own pull, smaller than Earth's, but large enough to alter motion across great distance. The Sun adds another influence from far beyond. In cislunar space, movement is never a straight act for long. Forward motion is always being bent into curves. For this reason, the region can be understood as a landscape without visible hills. Its slopes are made of gravity alone. They cannot be seen, yet they are real, and every object follows them. Light defines the region as clearly as gravity does. Between Earth and Moon, there is no atmosphere to soften sunlight into a blue sky. Surfaces turned toward the Sun receive direct brightness. Surfaces turned away fall into deep shadow. The boundary between light and dark can seem hard and sudden. Earth reflects sunlight outward from cloud tops, ice, desert, and sea. From this region, Earth appears bright, coloured, and alive with moving white systems. The Moon reflects light in a different way. Its surface is dry, dusty, and ancient. Broad dark plains lie beside brighter highlands, and the contrast records impacts from a very long past. In cislunar space, light is not gentle, it is clear, sharp, and exact. Heat also behaves differently here. On Earth, air and water move warmth from place to place. In open space, those common exchanges mostly disappear. A body warms by absorbing radiation and cools by releasing it. The result is an environment of extremes. A surface in full sunlight can become very hot. A surface in shadow can become intensely cold. The vacuum itself is not warm or cold in the familiar earthly sense. It cannot wrap around an object and carry heat away like wind. It simply allows radiation to rule. Exposure, therefore, takes on a different meaning. Without air, temperature becomes a matter of light, shade, material, and time. The vacuum changes more than heat. It also changes sound, pressure, and the basic conditions of existence. There is no ordinary sound in cislunar space because sound needs matter through which vibration can travel. No wind passes over an exposed surface. No outside air presses on metal. No liquid water remains stable in the open for long. The silence is absolute in physical terms, produced by near total emptiness. This emptiness is not harmless. It demands enclosure, pressure, and careful control from anything living or mechanical that enters it. Radiation is one of the most important features of the region. Earth helps protect nearby space through its magnetic field, which reaches outward and forms the magnetosphere. This magnetic shield deflects many charged particles, but not all of them, and its protection is not the same everywhere. Around Earth there are zones of trapped energetic particles called the Van Allen belts. Farther out, particles from the Sun move through space as part of the solar wind, and periods of solar activity can make conditions much stronger. Beyond that is cosmic radiation, high-energy particles arriving from deep space outside the solar system. Cislunar space is therefore invisible, but never inactive. It carries a changing population of energetic particles that matter greatly to exploration. Matter is present here in small amounts. Micrometeoroids cross the region at very high speed. Many are tiny, no larger than grains, yet speed gives them significance. Fine dust and plasma move through space in sparse distribution. Light itself exerts a slight pressure. Magnetic fields stretch and shift. None of these fill the region in a crowded way. The dominant impression remains openness. Still, openness does not mean simplicity. Cislunar space is thin, but it is not blank. It is quiet, but it is not inactive. Distance changes the sense of time in this region. On Earth, nearness is judged by roads, coastlines, or the horizon. Between Earth and Moon, scale is judged by travel time, orbital timing, signal delay, and changing position. Even light takes more than a second to cross the gap one way. That small delay is enough to remind the observer that space is not an abstract backdrop. It has measurable breadth, and that breadth shapes every relation within it. Earth may remain visible, bright, and familiar, yet it already belongs to another scale when seen from this distance. For all its severity, cislunar space is not hostile by intention. It simply follows its conditions with complete indifference. Earth turns, the moon circles, sunlight falls, shadows endure, radiation passes unseen, gravity shapes every curve. In this steady order, the Artemis II mission takes its place. It does not change the nature of the region. It moves within rules already set by mass, motion, light, and vacuum. The broad setting remains what it has long been, a vast corridor between two worlds, quiet in appearance, exact in behavior, and immense enough to make every human action within it seem careful, brief, and small. Before Artemis II becomes a path through deep space, it begins on Earth, the larger home world from which all its motion first takes meaning. Earth is not only the place where the crew lives, trains, and prepares. It is also the massive rotating body whose gravity must first be faced, whose surface conditions shape every hour of departure, and whose air, water, land, and weather define the first boundary of the mission. In the broad setting of the journey, Earth is the nearest and most familiar world. In the narrower setting of launch, it becomes a specific place with a coastline, a climate, a latitude, a season, and a turning day. Earth is a rocky planet wrapped in air and covered in broad oceans. Its diameter is a little more than 12,700 kilometers, large enough to hold a deep atmosphere close to its surface and strong enough to keep that atmosphere from drifting into space. This envelope of air makes Earth unlike the Moon, and unlike the open region beyond it. Air scatters sunlight into a bright sky. Water cycles through clouds, rain, rivers, and sea. Winds move heat from one place to another. Weather changes from hour to hour. Living things fill the surface. For a mission bound toward the Moon, these common earthly conditions are not background detail. They are the first environment that must be understood. The planet turns once in about 24 hours. This steady rotation changes the position of every launch site relative to the sky. It carries ground locations eastward, and at the equator that eastward motion is greatest. Florida lies north of the equator, but it still receives part of this turning advantage. A rocket launched eastward from the Florida coast begins its journey with a small gift from Earth's rotation. The effect does not remove the need for immense power, but it helps. In this way, even the planet's daily turning becomes part of mission design. A launch does not begin from a still platform. It begins from a world already in motion. The place associated with Artemis II is Kennedy Space Center on the Atlantic coast of Florida, near Launch Complex 39B. This is not an arbitrary choice of ground. Geography matters. The Florida Peninsula reaches southward into warm waters, placing the launch site closer to the equator than many other places in the continental United States. The coast also allows eastward flight over ocean rather than over densely inhabited land. This reduces risk during the earliest phase of flight and provides a broad corridor aligned with the practical needs of launch operations. The site carries history as well, but in physical terms its value comes from location, access, and the long development of facilities built to support large rockets. The land itself is low and flat. It rises only slightly above sea level. Marshes, lagoons, sandy ground, and coastal vegetation spread across the surrounding region. The Atlantic lies open to the east. Inland waters and wetlands shape local air and moisture. Heat builds quickly under sunlight, especially in the warmer months, and sea breezes often move inland as temperature differences grow between land and ocean. The atmosphere over this coastline is therefore active and changeable. It rarely behaves as a simple, uniform layer. Even before a vehicle leaves the ground, the conditions above the launch site are being shaped by sunlight, moisture, pressure, and the meeting of land and sea. Clouds are common in Florida. Some are shallow and harmless in appearance. Others rise into tall towers when warm. Moist air lifts rapidly upward. Lightning becomes a serious concern in such an environment. Thick cloud layers, rain bands, strong upper winds, and electrical conditions can all influence whether a launch proceeds. A spacecraft bound for the Moon may seem far removed from weather, but its departure still depends on weather in a very direct way. Earth's atmosphere does not surrender the mission easily. It asks for timing, patience, and repeated measurement. Meteorologists, engineers, and flight teams study local conditions because the path outward begins with the narrow agreement between machine and sky. Air pressure at the surface is another quiet but important fact of departure. At sea level, The atmosphere presses from all directions. Human bodies know this pressure so completely that it is rarely noticed. Vehicles and launch systems, however, must be built with exact knowledge of the outside air they will face while standing on the ground and rising through the lower layers above it. Temperature and humidity matter as well. Moist air behaves differently from dry air. Heat affects materials, fuels, electronics, and comfort for ground crews. Earth offers richness and life through its air and water, yet that same richness creates complexity for departure. The planet's gravity is the deepest local fact of all. Every structure at the launch site rests under its pull. Every litre of fuel, every cable, every metal surface, every human step exists within this downward force. On Earth, gravity is so constant that it becomes part of ordinary thought only when something tries to leave. Artemis II belongs to one of those rare attempts. The mission begins not in freedom but in weight. The vehicle stands fully burdened by the planet that made it possible. All planning at the surface begins from this condition. The launch site, the rocket, and the spacecraft are arranged beneath a sky that is held in place by gravity, on a planet that does not release anything without effort. Earth also shapes departure through timekeeping, day and night. Local weather windows, lighting conditions, and orbital needs all meet at the launch site. The ground team works within clocks, but those clocks reflect physical realities. Sun angle changes visibility and heating. Coastal weather evolves through the day. Winds shift with altitude and season. The mission may be aimed at the moon, yet the practical rhythm of departure is governed first by Earth's own cycles. Rotation sets the clock, atmosphere sets the conditions, geography sets the corridor, gravity sets the cost. In this way, Earth is not merely the world left behind. It is the full starting system of Artemis II. Its oceans help define the safe direction of travel. Its rotation offers momentum. Its coastal air demands caution. Its gravity gives the mission both its greatest restraint and its first source of meaning. The crew begins from a living planet of water, rock, cloud, and motion, standing on the edge of a continent beside the Atlantic, waiting within the measured calm that comes before departure. At the moment of ascent, the calm geography of the launch site gives way to a different region, still part of Earth, still close to the ground, but already defined by motion through air. Artemis II rises first through the lower atmosphere, where the vehicle does not yet move in the silent vacuum of space. It climbs through a dense fluid that presses against every exposed surface, flows around edges and seams, carries moisture, changes temperature with height, and turns speed into force. This is the first active environment of flight. It is not empty sky. It is a layered body of gas that resists motion even while allowing it. Near the surface, air is thickest. Most of the atmosphere lies in the lowest part, compressed there by gravity. Nitrogen and oxygen dominate its composition, with smaller amounts of argon, carbon dioxide, and water vapor. These gases seem light in daily life, yet together they create a substantial medium. A rising vehicle must push through it. At rest on the pad, the outside air presses from all sides. As ascent begins, that same air becomes a moving obstacle. The faster the vehicle travels, the more strongly the atmosphere responds. Pressure grows unevenly across the body of the craft. Air flows around curved surfaces, separates from sharp changes in shape, and leaves turbulent patterns behind. This lower atmospheric region, called the troposphere, is where weather lives. Clouds form here. Winds shift here. Moisture gathers and falls here. Temperature usually decreases with height in this layer, though not always at a perfectly steady rate. Warm and cool pockets of air may sit beside one another. Wind can change direction and speed from one altitude to the next. For a launch vehicle, this means ascent is never a simple upward movement through identical conditions. It passes through changing fields of pressure, density, and motion. Each change matters because even a small difference in airflow can alter the forces acting on a tall and rapidly accelerating structure. One of the first important effects is aerodynamic load. This means the push and pull created by air as the vehicle climbs faster through it. The load depends mainly on speed and air density. Near the ground, density is high, but speed is still building. Higher up, speed increases while density begins to fall. Between these conditions, there is a period when the combination becomes especially demanding. Engineers often describe this as the point of maximum dynamic pressure. Dynamic pressure is the pressure associated with motion through air. It is not the same as ordinary atmospheric pressure at rest. It is the added burden created by high speed in a fluid. During this period, the vehicle experiences some of its greatest aerodynamic stress. The atmosphere also produces heating, though not yet the intense heating of return from space. During ascent, air compresses and rubs around the outer surfaces. This creates warmth, especially on surfaces that face the flow most directly. The effect is strongest where air is still dense and speed is already high. The heating must be understood and managed, but it belongs to a different category from the fiery passage of re-entry. Here it is the steady result of rapid climb through thickening or thinning air, not the violent deceleration from orbital return. Even so, the thermal environment is real. Materials expand and contract. Surface temperatures shift. Sensors and outer structures must continue to function while surrounded by changing pressure and temperature. Vibration fills this region as well. The vehicle is not only moving through air, it is also producing immense thrust beneath it, and that thrust interacts with the atmosphere and with the structure itself. Combustion, exhaust flow, aerodynamic buffeting, and structural response combine into a complex field of shaking and oscillation. Some vibrations are low and broad, passing through large parts of the vehicle. Others are finer and more rapid, affecting panels, instruments, and connections. The lower atmosphere amplifies some of these effects because air can carry pressure waves and feed unstable motions. The result is a demanding mechanical environment in which the vehicle must remain controlled, intact, and accurately guided. Sound, in ordinary experience, belongs to the launch environment because air allows pressure waves to travel. Near the pad, the power of ascent creates extremely strong acoustic energy. That energy reflects from surfaces, moves through structures, and can affect hardware if not carefully managed. Yet once the vehicle climbs higher, the character of this acoustic environment changes with thinning air. The atmosphere still carries pressure waves, but less effectively as density falls. In this way, ascent passes through a region where air not only resists motion, but also transmits force in forms that are felt through vibration and pressure. Winds are among the most variable features of the lower atmosphere. At one height, the air may drift gently. At another, it may move strongly across the flight path. Wind shear, which means a rapid change of wind speed or direction over a short vertical distance, can place special demands on a rising vehicle. A tall launch system responds to such changes with bending and correction. Guidance systems can adjust, but the atmosphere still sets the initial problem. The vehicle is not crossing a still column, It is moving through a shifting river of air stacked in layers. As the climb continues, the atmosphere begins to thin. Pressure falls with altitude. Air molecules become less crowded. Aerodynamic load begins to ease even as speed continues to increase. The vehicle enters a transition in which the lower atmosphere loosens its hold. The sky darkens gradually. Weather is left below. The direct influence of dense air begins to fade. Yet this change is not sudden. There is no sharp line where flight in air simply ends. Instead, there is a long reduction in density, drag, and convective heating, step by step. The vehicle leaves the deepest part of Earth's gaseous envelope. Throughout this ascent region, the human experience inside the vehicle is shaped by acceleration and vibration, but the underlying cause remains the surrounding atmosphere acting together with thrust. The crew is still close to Earth in physical terms, though distance from the pad grows quickly. They are moving upward through the last substantial layers of the planet's air, carried by a machine that must answer every demand the atmosphere makes. Pressure presses, wind shifts, heat rises on outer surfaces, vibration travels through the frame, speed increases. The lower atmosphere tests the ascent not through intention, but through its ordinary physical nature. In this region, Earth still holds the mission closely. Air is the final great earthly substance through which Artemis II must pass before space begins to resemble the wider cislunar quiet beyond. The launch environment is therefore not a brief interruption between ground and space. It is a full and consequential layer of the journey, dense with force, measurable in gradients of pressure and speed, and governed by the simple fact that to leave Earth, a craft must first climb through the moving ocean of air that surrounds it. The broad forces of ascent become visible through the machine that carries them. For Artemis II, that machine is the Space Launch System, the large launch vehicle built to lift a crewed spacecraft away from Earth and place it on a path toward the Moon. In outward appearance, it is a tall, narrow structure of metal, insulation, tanks, engines, and boosters, arranged in a straight vertical form that stands against the sky with unusual stillness before flight. Its purpose is simple to state and difficult to achieve. It must raise a spacecraft from the ground, carry it through the atmosphere, continue upward into near vacuum, and provide enough speed and energy for the journey beyond low Earth orbit. The vehicle is therefore not a single engine with a capsule above it. It is a layered system in which each major part serves a distinct role in the lifting process. At the center stands the core stage, the largest main body of the rocket. This long cylindrical section forms the structural spine of the vehicle during the early phase of ascent. It contains the main liquid propellants needed for sustained powered flight after liftoff. Near the lower end are 4 main engines, arranged in a square pattern and gimbaled so that they can pivot slightly to help steer the vehicle. These engines burn liquid hydrogen and liquid oxygen, a combination long used in high-performance launch systems because it provides strong efficiency, though it requires extremely low storage temperatures. Liquid hydrogen is very light and must be carried in a very large tank. Liquid oxygen is denser and occupies less volume for a given mass. Together they fill much of the core stage interior. The engines at the base of the core stage are RS-25 engines, descendants of the main engines once used on the space shuttle. Their shape is compact compared with the scale of the rocket above them, but their effect is immense. Each engine draws propellant through turbopumps, mixes the fuel and oxidizer in a combustion chamber, and expels hot gas through a nozzle at very high speed. The physics is direct. Gas forced downward produces thrust upward. Yet the machinery required to do this in a controlled and sustained way is extremely refined. High pressure, cryogenic temperature, precision timing, and stable combustion all have to exist together. The engines must begin in sequence, reach full operating conditions, and continue through ascent while the entire structure around them is accelerating and vibrating. Attached to the sides of the core stage are two solid rocket boosters. These are large, white, segmented motors that provide much of the thrust at liftoff and during the earliest phase of flight. Their role is especially important near the ground, where Earth's gravity is strongest and the atmosphere is densest. A heavy launch vehicle needs very great force at the moment it begins to rise, and the boosters help supply that force. Unlike the core stage engines, which burn liquid propellants fed through lines and pumps, the boosters contain solid propellant cast within their long cases. Once ignited, the propellant burns in a controlled pattern until it is used. This means the boosters are powerful and mechanically simpler in some respects than liquid engines, though they cannot be throttled in the same flexible way. The presence of these side boosters gives the space launch system much of its visual identity. They widen the lower half of the stack and make clear that the launch vehicle is not a single tube but a combined structure. At liftoff, flame and exhaust emerge both from the boosters and from the core stage engines. The total thrust is enough to raise the fully loaded rocket slowly from the pad and then accelerate it upward with increasing speed. The first movement may appear deliberate and almost restrained, but this restraint belongs only to appearance. The forces involved are enormous. The vehicle begins its climb because the combined thrust exceeds its weight, and once that threshold is crossed, the rocket becomes a rising system of controlled combustion. Above the core stage sits the upper stage used for Artemis II, called the interim cryogenic propulsion stage. This section is smaller in diameter than the core stage and serves a different part of the mission. It does not dominate the earliest visual impression because it rests higher in the stack and works later in flight. Even so, it is essential. After the lower parts have done their work and separated, the upper stage provides the additional impulse needed to place the spacecraft on the proper trajectory beyond Earth orbit. It carries its own cryogenic propellants and a single RL-10 engine, a long-used engine type known for efficiency and precision in upper stage operation. Where the lower parts of the rocket are associated with brute lifting power, the upper stage represents a quieter and more exact contribution, adding energy where timing and direction matter greatly. Between these major elements are interstages, attachment structures, feed lines, avionics, and protective systems that allow the whole vehicle to behave as one machine rather than as separate parts merely stacked together. Loads must pass through the structure from one section to another. Guidance commands must reach the engines. Sensors must report pressure, temperature, acceleration, and orientation. Tanks must remain within safe conditions. The rocket stands as a continuous body, but internally it is a carefully organized arrangement of functions. Structural strength, propellant storage, control, ignition, separation, and telemetry all occupy their own places within the larger design. The outer surfaces of the space launch system show traces of these internal realities. The orange color of the core stage comes from spray-on thermal protection over the tank structure, a practical covering rather than a decorative one. White sections mark the boosters and other outer elements. Lines, joints, access points, and attachment fittings break the simplicity of the cylindrical shape. The rocket appears clean in outline, yet close observation reveals how much hardware is needed to support controlled ascent. Every visible form belongs to load, flow, protection, or connection. Scale is one of the most important facts of the vehicle. It is not merely tall by ordinary standards. It is tall because it must contain large volumes of propellant, engines able to use that propellant effectively, and a stacked arrangement that places the crewed spacecraft above the most violent lower forces of launch. Height allows tanks, stages, and payload to be arranged in a vertical sequence suited to flight. Mass allows momentum, structure, and endurance through ascent. The vehicle is large not for spectacle, but because leaving Earth with a crew and lunar mission equipment demands size at every level. In this outer machine, the aim of Artemis II becomes physical. The mission is no longer only a plan traced on paper or a destination imagined beyond Earth. It becomes a launch vehicle composed of thrust, tankage, engines, boosters, and structure, all shaped for one task. The Space Launch System stands as the great lifting form of the mission, a temporary tower of stored energy and controlled force, built to transform a spacecraft at rest on Earth into a body moving outward toward the Moon. Once the launch vehicle has done its lifting work, attention narrows from the great rocket to the spacecraft it has carried upward. Orion appears not as a single smooth capsule alone, but as a joined form designed for travel beyond low Earth orbit. Its outer shape is the visible answer to several demands at once. It must separate cleanly from the larger vehicle, remain stable in deep space, connect at its forward end with other systems when needed, and preserve a form that can return safely to Earth. The result is a spacecraft whose appearance is simple from afar and highly deliberate at closer range. The most familiar part is the crew module, the forward body often described as the capsule. In outline, it is neither a sharp cone nor a perfect bell. It is a blunt conical form with gently sloping sides that widen downward to a broad circular base. This shape comes from long experience in human spaceflight. For a crewed craft that must one day re-enter Earth's atmosphere from great speed, a blunt body offers important advantages in stability and thermal behavior. Even while Orion travels quietly in space, the outer form already carries the logic of that requirement. Its geometry is calm in appearance, but purposeful in every line. Seen from the side, the crew module looks compact and strong. It does not stretch into a long cylinder. Instead, it gathers volume into a short pressure vessel, deep enough to contain living space and equipment, yet externally held within a shape that presents no unnecessary extension. The outer surface curves continuously from the forward end down toward the wider aft edge. Smooth transitions reduce abrupt changes in structural load and help the spacecraft behave as a single body, rather than as a collection of protruding parts. At the front is the docking system, set into the forward end like a carefully prepared face. This area gives Orion a sense of direction even when the spacecraft drifts in silence. The docking ring and hatch arrangement define the topmost point of the crew module and establish the forward axis of the vehicle. During launch, it sits protected within the larger launch configuration, in space. Once the launch abort system is gone, the forward end becomes visually clear. It is flatter than the sloping sides below, and it serves as the formal front of the craft. This area is central to the visual identity of Orion because it marks the place where connection, approach, and alignment are most exact. Around the forward region are windows that alter the otherwise continuous shell. Orion does not carry large sweeping panes. Its windows are few, placed with care, and shaped for strength as much as for view. NASA has described 4 windows on the crew module backshell cone, with additional windows in the docking hatch and side hatch. From outside, These openings interrupt the exterior just enough to remind the observer that the craft is not only a vehicle, but also a place of human presence. The windows are small by earthly standards because the surrounding structure must remain strong, sealed, and dependable. Yet even their limited size gives the spacecraft a more intimate character. The side hatch also belongs to the outer form, though it is less dominant in distant views than the windows or forward docking area. Its outline is fitted into the crew module shell as a practical opening for access on the ground, and for operations when the spacecraft is not enclosed within launch hardware. Like the windows, the hatch must join human use to structural integrity. Its presence reveals that the outer skin is not continuous by accident, but carefully divided into areas that open, seal, align, and endure. Below the crew module, the spacecraft narrows into the connection with the European service module. This union changes the silhouette. The upper portion remains the blunt, crude body, while the lower portion becomes more cylindrical and openly mechanical in appearance. In the complete spacefaring form of Orion, the service module is visibly distinct. Solar array wings extend outward from it in a cross-like arrangement, long and flat against the darkness when seen deployed in space. These wings make the spacecraft appear wider and more delicate than the crew module alone would suggest. They add span without adding heaviness. This contrast is one of the most striking features of Orion's outer form. The crew module looks dense, enclosed, and protective. The service module and its appendages look functional, extended, and exposed. Together they create a spacecraft balanced between shelter and utility. The front is blunt and inhabited. The rear is narrower and more openly mechanical. The solar arrays, each made of several rectangular panels, introduce straight lines into a design otherwise dominated by curves and circles. Their slow turning toward light gives the vehicle a quality of orientation. Surface texture also helps define Orion from the outside. The crew module does not present a polished aircraft skin. Panels, seams, attachment points, covers, and thermal blankets create subtle variation across its exterior. Some areas appear smoother, others show layered protection or hardware mounted close to the hull. These features are the visible record of a spacecraft built to work in vacuum, sunlight, shadow, and radiation. Close views reveal that even a simple conical body requires many boundaries between materials and many transitions from one exterior function to another. In distant images, Orion can seem modest in size when compared with the vast rocket that first carries it. Yet once separated from that launcher, its outer form becomes sufficient in itself. It no longer appears as a payload riding above something larger. It appears as an independent craft, proportioned for deep space travel rather than spectacle. The compact crew module, the formal forward docking end, the carefully placed windows, the attached service module, and the long solar wings together create a profile that belongs specifically to missions beyond near-Earth orbit. Its appearance expresses a central principle of the Artemis era. The spacecraft is built not only to leave Earth, but to remain capable far from it. Every visible part of the outer form supports that idea. The body is enclosed where people must be protected. The front is prepared for precise alignment and access. The lower section carries the structures needed for sustained travel. The wings reach outward to gather light. Nothing in the design appears ornamental. Orion's outer form is therefore a clear exterior statement of purpose, a human spacecraft made to move through deep space with stability, economy, and quiet assurance. The outer form of Orion is only the first layer of meaning. Beneath the visible shape lies a second outer reality, made of materials chosen not mainly for appearance or structure, but for survival, section by section, panel by panel. The spacecraft's exterior is covered, thickened, sealed, or shielded according to the conditions it must face. In the quiet of deep space, these protections may seem passive, almost still. Yet each one is designed for an environment that can be severe in a different way. Sunlight can overheat exposed surfaces. Shadow can drive temperatures sharply downward. Tiny particles can strike at great speed. During return to Earth, air itself becomes a source of intense heating. Orion therefore carries not one kind of outer protection, but a set of protective layers arranged according to location, direction, and expected stress. The most important of these is the heat shield at the base of the crew module. It forms the broad circular underside of the spacecraft, the largest single protective surface on the crewed capsule. This is the side that will face the greatest thermal burden during return to Earth, while the crew module in space appears calm and compact. The lower face already carries the logic of that future passage. Its size, thickness, and composition are all defined by the need to endure the energy released when a spacecraft returning from the Moon meets the atmosphere at very high speed. Orion's heat shield uses a material called avcoat. Avcoat is an ablative material, which means it protects by slowly breaking down in a controlled way under extreme heating. Rather than remaining unchanged, it accepts damage as part of its function. Heat drives chemical and physical change within the material. Some of the outer layer chars, recedes, and carries energy away from the spacecraft. This may seem destructive, but it is protective destruction, deliberate in concept and carefully bounded in practice. The heat shield does not defeat heating by staying untouched. It defeats heating by sacrificing part of itself in an ordered manner, so that the deeper structure and the cabin above remain within safe limits. This idea gives the heat shield a very different character from ordinary strong surfaces. A steel plate is often imagined as protective because it resists change. Orion's heat shield protects because it changes in the right way. Its outer face is made to be consumed slowly rather than to remain perfectly fixed. The material must char, vent, and erode according to expected loads. It must also remain attached, shaped, and predictable while doing so. Protection here is not simple hardness. It is managed transformation. The shield is not a single-pored piece spread as one continuous blanket. Orion's heat shield is covered with blocks or tiles of avcoat fitted across its outer surface. This approach allows the material to be manufactured, inspected, and installed with high precision across the wide curved base of the capsule. The shield itself is about 16.5 feet across, a dimension that gives it broad authority over the entire lower face of the crew module. Every part of that circular surface belongs to the same thermal task, but the loads are not perfectly uniform across every location. The arrangement of ablative material must therefore answer both the overall mission need and the detailed variations expected across the surface. Behind the ablative layer is the supporting structure of the crew module, which the outer material exists to protect. The shield is not the spacecraft by itself. It is the exposed sacrificial barrier placed ahead of more durable layers and the inhabited volume above them. This relationship is important. Orion's outer protection is designed in depth. One layer meets the environment first. The next layer remains cooler and more stable, because the first has done its work. Safety comes from the stack of functions, not from any single surface alone. The heat shield is only the most dramatic part of the thermal protection system. Around the sides of the crew module, the back shell carries its own protective materials. These side surfaces do not receive the same direct thermal load as the broad base during return, but they still face strong demands across launch, spaceflight, and atmospheric entry. Their protection must account for sunlight, cold shadow, mechanical stress, and changing thermal conditions. The backshell is therefore covered with carefully chosen outer materials, blankets, coatings, and structural skins that manage heating and cooling while preserving the shape and integrity of the capsule. Near the forward end, another protective outer element appears in the form of the forward bay cover. This covering protects important systems in the nose region during phases when they are not meant to face the full outside environment. Its presence shows that not all external protection is permanent in the same way. Some barriers remain with the spacecraft throughout flight, others serve for a defined phase and are later removed or no longer needed. Protection, in Orion's design, is therefore both fixed and timed. A surface may guard against launch debris, heating, pressure changes, or exposure only until the mission enters a different condition. External protection also includes shielding against the smaller hazards of deep space. Micrometeoroids and tiny fragments can strike at speeds high enough to matter, even when their size is very small. Not every outer surface is equally exposed, and not every part of the spacecraft requires the same level of barrier, but the general principle remains clear. The spacecraft must expect occasional impact from a sparse but real environment. This means outer materials are chosen not only for temperature, but also for resistance, spacing, layering, and controlled damage tolerance. A surface may not need to remain flawless. It needs to remain functional. Thermal control on the exterior often depends on color, finish, and surface properties as much as on bulk thickness. Some coverings reflect more sunlight, some release absorbed heat more effectively, some insulate what lies beneath, in space, where heat is gained and lost mainly by radiation. These properties become especially important. Orion's exterior therefore works at two very different scales at once. At the large scale, the capsule carries a major ablative shield for return. At the finer scale, it uses specialized outer finishes and layered coverings to regulate the slow, constant exchange of heat in sunlight and darkness. The lessons of earlier testing and flight have given this protective system added importance. Orion's heat shield has been studied extensively, and NASA has publicly described findings from Artemis I, including unexpected char loss linked to gases in the AV coat that did not vent as expected during re-entry. For Artemis II, NASA has continued preparing Orion with the heat shield already attached to the capsule, while using those findings to inform understanding and readiness. This gives the shield a particular significance for the first crewed Artemis mission around the Moon. It is not only a protective layer in theory, it is a closely examined and mission-defining surface whose performance matters directly to the safe return of the crew. In Orion's outer protections, endurance takes material form. The shield beneath, the protected sides, the covered forward region, and the carefully finished exterior together express a single idea. A spacecraft going far from Earth must survive not by ignoring its environment, but by meeting each condition with the right outer layer. Orion carries that principle over its entire skin. It is clothed for heat, cold, impact, and exposure. A crewed vessel whose calm exterior conceals a long preparation for extremes. Behind the crew module, joined to it in a firm and carefully engineered union, the European Service Module forms the working body of Orion. If the crew module is the protected human chamber, the service module is the supporting engine room that keeps the spacecraft active and sustained in deep space. Its role is less visible in popular imagination than the capsule at the front, yet its contribution is constant and essential. It provides the quiet functions without which the crewed portion could not travel far from Earth. Electricity, propulsion support, thermal control, water, oxygen, and nitrogen all depend on this attached section. In outward appearance, it is more mechanical than the crew module. In practical meaning, it is the part that feeds, steadies, and drives the larger whole. The service module sits directly aft of the crew module and extends the spacecraft backward into a more open and functional form. Where the crew module gathers people inside a strong pressure vessel, the service module spreads necessary systems across an exposed structural frame. Tanks, engines, radiators, lines, electronics, and solar arrays all belong to it. The contrast is immediate. The front of Orion looks enclosed and sheltering. The rear looks arranged for work. This difference is not a divide between important and unimportant parts. It is a divide between two kinds of necessity. One part houses the crew. The other part supports their survival and motion. Its name reflects this supporting purpose. In spacecraft language, a service module is the section that provides the services required for mission operation. In Orion, those services are broad. The module stores and distributes water for the crew. It carries gases used to support the cabin environment. It generates electrical power through solar arrays rather than depending only on stored battery energy for the whole mission. It also helps keep temperatures within acceptable limits by moving heat and releasing it through radiators into space. Most importantly, in structural and mechanical terms, it carries the propulsion hardware that allows the spacecraft to alter its path and orientation. The word European in its name is equally important. This module is the contribution of the European Space Agency to the Orion spacecraft, built through European industry and integrated into an American crewed mission architecture. The result is not symbolic cooperation alone. It is a direct material partnership placed at the heart of the vehicle. A crewed spacecraft for a mission around the Moon depends in practical daily operation on systems provided across this international collaboration. The service module, therefore, has a dual identity. It is a machine section within Orion, and it is also a visible expression of shared work across agencies and nations. Structurally, the module acts like a supporting chassis behind the crew capsule. It helps carry loads between the crew module and the launch vehicle during ascent, and later it remains the main external framework for many spacecraft functions once Orion is flying freely in space. This means the service module must be strong without becoming excessively heavy. Its structure has to endure launch vibration, vacuum exposure, temperature cycling, and the steady burden of attached tanks, thrusters, electronics, and arrays. It is not shaped for re-entry like the crew module. It is shaped for sustained operation in space. One of its most recognizable outer features is the set of 4 solar array wings. When deployed, they extend outward from the service module and give Orion a broader, almost cross-shaped silhouette. These arrays gather sunlight and turn it into electrical power for the spacecraft. Their presence changes the visual meaning of Orion. The vehicle no longer appears as a sealed capsule alone. It becomes a system that reaches outward into the environment to collect the energy it needs. The arrays are light compared with the main bodies of the spacecraft, but they are central to its endurance. In the long, dark background of space, they represent the steady conversion of sunlight into the current that feeds onboard systems. The service module also contains tanks for water and gases needed by the mission. These stored materials make the module feel less like an engine alone and more like a support vessel attached to the cabin. Water is not only for drinking, it also participates in the broader life support needs of a crewed mission. Oxygen and nitrogen relate to the cabin atmosphere, pressure management, and the continued maintenance of a habitable inner environment. The crew inside the forward module may not always see these stores directly, yet their presence in the service module is one of the reasons the spacecraft can function as a living system rather than as a mere transport shell. Thermal control belongs here as well. In deep space, a spacecraft cannot rely on air or wind to remove excess heat. Internal electronics, power systems, and other equipment continuously produce heat that must be managed. The service module carries radiators and fluid systems that help gather this unwanted thermal energy and release it into space. This work is quiet and continuous. Without it, temperatures and important systems could move beyond safe limits. Thermal control is therefore part of the sustaining character of the module. It does not attract attention in the dramatic way that engines do, but it is one of the steady forms of care the spacecraft performs for itself. Propulsion hardware occupies another major portion of the service module. It carries the main engine and the smaller thrusters needed for spacecraft movement and control. Although the detailed actions of these systems belong to the next inner layer of understanding, their physical home is here. This makes the service module both a supply section and a motive section. It stores what the spacecraft needs to live, and it contains what the spacecraft needs to act. In this way, it resembles the hidden working spaces of a ship more than the visible bridge. The crew module may hold the astronauts, but the service module provides much of the capability that allows the entire craft to function with purpose. There is also a temporary quality to the service module that shapes its meaning. It supports Orion throughout deep space flight, but it is not intended to survive the final return through Earth's atmosphere with the crew. Before re-entry, the service module separates, leaving the crew module to descend alone beneath the protection of its heat shield. This gives the service module a specific place in the life of the mission. It is a faithful companion section for the journey outward and back through space, but not for the final passage into the air. It exists fully for the spacefaring phase of Orion's work. Taken as a whole, the European service module gives Orion depth as a spacecraft. It adds power, supplies, structure, cooling, and propulsion support to the protected human capsule at the front. It transforms the vehicle from a survivable cabin into a self-sustaining exploration craft. Quietly attached behind the crew, it does not ask to be seen first, yet in the inner logic of the mission, it is indispensable. It is the working rear body of Orion, the steady provider of motion and support, and the living machinery that allows a human spacecraft to remain capable far beyond Earth. Within the service module, support becomes action, the same rear body that stores water, gases, and heat control hardware also contains the systems that give Orion the ability to move with precision and remain electrically alive through the mission. These are not the large visible features that first define the spacecraft from afar. They are working systems, often hidden inside structure, tanks, lines, and housings, yet they are active almost continuously. They shape how Orion turns, how it holds its attitude, how it changes its path, how it powers its instruments, and how it manages the limited stores on which a deep space journey depends. In this inner region of the spacecraft, motion and power are not dramatic events alone. They are steady disciplines of measurement, release, correction, and balance. The first of these disciplines is propulsion. In simple terms, propulsion means the controlled use of mass expelled from the spacecraft to change the spacecraft's own motion. Orion cannot push against air in space because there is almost no air there. It cannot depend on wings or wheels. To turn or to alter its path, it must throw mass away in the desired opposite direction. This is the governing rule behind its motion systems. Gas and hot exhaust move outward. The spacecraft responds by shifting in attitude or velocity. Every correction, large or small, belongs to that principle. At the center of Orion's propulsion system is the main engine carried on the service module. This engine provides the larger changes in velocity needed at important moments in the mission. It is not used in a constant burning way like the engines of the launch vehicle during ascent. Instead, it is held in reserve for carefully timed firings. Each one planned to alter the spacecraft's trajectory by a measured amount. Its role is therefore deliberate rather than continuous. The main engine gives Orion the capacity to make meaningful changes in its path when precision matters more than raw thrust duration. Around this larger engine are smaller thrusters that serve different levels of control. Some are used for medium changes in motion and for important spacecraft maneuvers that do not require the full authority of the main engine. Others are reaction control thrusters, used for fine pointing and attitude control. Attitude means orientation, the direction in which the spacecraft is facing. A craft in deep space may need to turn its nose, rotate around its long axis, or hold a stable position relative to the Sun, Earth, or Moon. These changes do not always require a major engine firing. Often they are accomplished by short bursts from smaller thrusters placed around the service module in balanced arrangements. The effect of these small thrusters can seem almost modest, yet in the near emptiness of space they are highly effective. A brief pulse can begin a slow turn, another pulse can stop it. A sequence of carefully timed firings can rotate the spacecraft to a new attitude with remarkable accuracy. This kind of control matters constantly. Solar arrays may need the right angle to gather light efficiently. Antennas may need proper orientation for strong communication. Instruments and windows may require stable pointing. Even thermal control can depend partly on how the spacecraft is oriented relative to sunlight and shadow. Motion, in Orion, is not only about traveling from one place to another, it is also about keeping the spacecraft properly arranged within its environment. Fuel and oxidizer storage therefore become part of the deeper logic of movement. The propulsion system can act only if propellants remain available in the right condition and can be delivered through lines, valves, and pressurized systems when needed. Tanks hold the chemical resources for motion just as other tanks hold resources for life support. This creates an economy of action. Every burn consumes finite stores. Every correction draws from a limited budget. The spacecraft cannot move without thought. It must move with discipline, conserving propellant while still preserving safety, pointing accuracy, and mission goals. The same principle of disciplined use applies to electrical power. Orion gathers much of its electricity through the solar arrays mounted on the service module. Sunlight falls on the cells in the arrays and is converted into electrical current. That current is then conditioned, distributed, and used across the spacecraft. Some of it powers computers, communications equipment, sensors, lighting, pumps, heaters, and control systems in real time. Some can be used to charge batteries for periods when direct sunlight is less available, or when demand briefly shifts. In this way, power is not a single store waiting to be spent. It is a flowing system, continuously generated, routed, regulated, and watched. Electrical power in a spacecraft must be stable. Instruments and computers depend on voltage and current remaining within acceptable ranges. Too little power can shut down important functions. Too much or poorly regulated power can damage hardware. Orion's electrical system therefore includes conversion and control equipment that turns sunlight from the arrays into usable forms for the vehicle's different needs. It also distributes that power according to priority. Some systems are always essential. Others may be reduced, cycled, or timed according to mission conditions. Resource management becomes part engineering, part discipline, and part daily rhythm. Batteries add another layer of resilience. Solar arrays provide the main long-duration source of electrical energy, but batteries help the spacecraft bridge conditions when generation and demand do not align perfectly. They also support periods when the arrays are not yet deployed, or when power needs require temporary supplementation. This means Orion carries not only the ability to gather energy, but also the ability to store and release it in a controlled manner. The spacecraft becomes, in this respect, an energy system as much as a transport vehicle. Because power and motion are so closely linked, the spacecraft must manage them together. Thruster valves require electricity to open and close under command. Guidance computers need stable power to calculate orientation and control firing sequences. Heaters may be needed to keep propellant lines and tanks within acceptable thermal ranges. Solar array pointing affects how much electricity is available, and attitude decisions may reflect that fact. Nothing in this inner system works in isolation. Motion supports power collection. Power supports motion control. Both rely on careful timing and constant monitoring. This constant monitoring is one of the quiet achievements of Orion's design. Sensors report tank conditions, pressures, temperatures, electrical status, and spacecraft orientation. Computers compare actual behavior with commanded behavior. Small errors are identified and corrected before they grow into larger problems. The spacecraft therefore maintains itself not by remaining inactive, but by performing continuous small acts of adjustment. Deep space travel may look serene from a distance, yet inside the service module it is sustained by a patient and almost unbroken stream of control. The power and motion systems of Orion show how a spacecraft remains capable over time. They transform stored propellants into trajectory changes, brief thruster pulses into stable orientation, sunlight into electricity, and electrical flow into the living function of the whole vehicle. Nothing in these systems is extravagant. Their purpose is measured continuity. They keep Orion pointed, supplied, responsive, and alive as a working machine. In the silent reach between Earth and Moon, that quiet constancy is one of the deepest forms of strength. Beyond the visible structure of Orion and behind the steady work of propulsion and power lies another inner layer of the mission, one made not of large surfaces or stored materials, but of information. A spacecraft traveling between Earth and the Moon must know where it is, how it is oriented, how fast it is moving, and whether the path it follows still matches the path intended. At the same time, people on Earth must know many of those same things from far away. This need creates a network of navigation and communication, partly on board and partly spread across space and ground stations, in which timing, radio signals, sensors, and calculation hold the mission together. In deep space, the spacecraft is physically distant, but it is never meant to become unknown. Navigation begins with state knowledge. This means an understanding of the spacecraft's condition in motion position, velocity, and attitude. Position describes where Orion is relative to Earth, the Moon, and other reference frames. Velocity describes how fast and in what direction it is moving. Attitude describes how it is pointed. These three ideas are linked. A spacecraft can be on the right path but facing the wrong way. or pointed correctly while drifting slightly off course. Accurate flight therefore depends on all three being measured, updated, and interpreted together. Part of this knowledge comes from instruments inside Orion itself. The spacecraft carries inertial measurement systems that detect motion through carefully monitored changes in acceleration and rotation. Inertial means based on the tendency of a body in motion to continue according to the laws of mechanics unless acted upon. An inertial system does not need to look outside first in order to sense that a turn or acceleration has taken place. It feels those changes from within the spacecraft. This makes it valuable because it can continue functioning even when outside references are temporarily unavailable or less convenient. It provides continuity, a kind of inner memory of motion, yet no inner memory remains perfect forever. Small uncertainties grow with time. Tiny measurement errors can slowly accumulate. For this reason, Orion also uses outside references. Stars provide one of the most stable of these references. Star trackers can observe known stars and compare their measured locations with stored patterns. From this comparison, the spacecraft can determine its attitude with very high precision. The stars do not guide Orion in the sense of pulling it along a route, but they give orientation in a region where there is no up, down, left, or right in the earthly sense. A spacecraft can turn toward them and recover a trustworthy sense of how it is aligned within space. The Sun and Earth can also serve as references under suitable conditions. Their brightness and known positions contribute to orientation solutions when combined with other measurements. The Moon becomes an important reference as Orion draws nearer to it. Navigation is therefore not based on one sensor or one source alone. It is based on agreement among measurements, internal motion sensing, external observation, timing, and radio tracking all contribute pieces of the larger answer. Confidence grows when those pieces fit together. Time is one of the quiet foundations of navigation. A deep space mission depends on very careful clocks. Signals need timestamps. Trajectory calculations depend on when a burn begins and ends. Position estimates improve when the exact timing of transmitted and received signals is known. Even a small error in timekeeping can translate into uncertainty in distance or motion. Clocks aboard the spacecraft and clocks on the ground therefore become partners in the same system of knowledge. They do not merely mark the passing of hours, they define the precision with which events can be understood. Communication carries much of this knowledge by radio. Orion sends and receives information through antennas that translate electrical signals into electromagnetic waves and back again. These waves travel through space at the speed of light. That speed is extremely great, yet the distance between Earth and the Moon is large enough that delay becomes noticeable. A message does not arrive instantly. Commands sent from Earth take time to reach the spacecraft. Telemetry, which means the automatic transmission of measured data, also takes time to return. This delay is not large enough to isolate the crew, but it is large enough to remind everyone that deep space communication belongs to real distance. The information carried in these signals is varied. Some of it concerns spacecraft health temperatures, pressures, electrical status, propellant quantities, computer states, and countless other measurements. Some of it concerns motion attitude, trajectory data, and the results of navigation solutions. Some of it concerns crew voice and operational coordination. Together, these transmissions create a moving portrait of Orion's condition. The spacecraft speaks continuously in data, and the ground responds with interpretation, support, and when needed, updated instructions. Ground-based tracking plays a major role in this process. Large antennas on Earth listen for Orion's radio signals and send signals back. By measuring how long a signal takes to travel, and by studying changes in frequency caused by relative motion, flight teams can estimate distance and velocity with high accuracy. Frequency shift is often called the Doppler effect. It means that motion between transmitter and receiver slightly changes the observed frequency of the radio wave. From that shift, motion along the line of sight can be inferred. This is an elegant feature of deep space tracking. A signal used for communication also becomes a tool for navigation. Communication is not only about reaching Earth, it is also about maintaining order inside the mission. Commands must be formatted correctly. Data must be organized so that important information is not lost in the larger flow. Antennas must be pointed appropriately. Power must be available to transmit. The spacecraft must therefore manage communication as part of its daily function. A radio link is not a simple, invisible thread that exists without care. It is a system sustained by hardware, timing, orientation, and disciplined procedure. Autonomy becomes important here as well, because signals do not move instantly, and because some moments require fast local decisions. Orion cannot depend on constant direct human control from Earth for every small action. Onboard computers must execute stored guidance logic, manage routine control tasks, and preserve spacecraft stability between contacts or during communication delays. This does not remove the role of ground teams. Instead, it creates a partnership. Earth provides broad supervision, trajectory support, and mission judgment. The spacecraft provides immediate self-management based on its sensors and programming. Navigation and communication therefore meet in a shared architecture of trust. All of this remains invisible from outside. No large motion announces it. No dramatic surface reveals it. Yet the mission depends on it as surely as it depends on engines or shields. Navigation keeps Orion known to itself and to Earth. Communication prevents distance from becoming separation. Timing binds measurement to reality. Radio carries both technical fact and human presence across the dark interval between worlds. In this inner layer of Artemis II, the spacecraft moves not only through space, but through a continuous exchange of information, where knowing and being known are essential parts of the journey. Once Orion can sustain itself, orient itself, and remain known across distance, the mission narrows again from systems to path. Artemis II does not simply go outward in a loose sense. It follows a carefully designed route shaped by gravity, timing, and speed. This route is often described as a translunar trajectory, meaning the path from Earth toward the Moon. Yet the phrase contains more than distance. It describes a moving curve through a gravitational landscape in which Earth first dominates, then gradually yields influence as the spacecraft approaches the region where the Moon matters more strongly. The path is therefore not a straight line drawn between two spheres. It is a calculated arc through changing conditions of motion. The beginning of this path comes after the launch vehicle has lifted Orion away from Earth, and the upper stage has given the spacecraft the velocity needed to leave low Earth orbit. Velocity means speed with direction. A spacecraft may move very fast and still fail to reach the Moon if that speed is pointed wrongly or given at the wrong time. Translunar flight depends on both amount and direction. The spacecraft must receive enough energy to climb outward from Earth's gravitational hold, but not in a careless or excessive way. Too little energy leaves it short of the intended path. Too much changes the geometry of the mission and the demands of later correction. The translunar route begins. Then, with a carefully tuned departure from the nearer Earthbound region, into a broader curve extending outward. This curve is governed first by Earth. Even when Orion is moving away at great speed, Earth still pulls on it continuously. The spacecraft is not escaping gravity. It is moving within gravity, using its laws rather than resisting them. As Orion climbs farther from Earth, some of its outward speed is gradually exchanged for altitude in the gravitational field. It rises in the same general sense that a thrown object rises above the ground, though here the scale is vastly larger and the path is orbital rather than local. The spacecraft moves outward because it has been given enough energy to do so, but Earth's pull steadily reshapes the motion into a long bent arc. Along this path, time and location are inseparable. A burn performed earlier or later changes where the spacecraft will be hours and days afterward. The same amount of velocity added at the wrong moment can produce a different route. This is why the translunar path is often described not just as a line in space, but as an event in time. The Earth, Moon, and spacecraft are all moving. The Moon will not remain in one fixed place waiting to be reached. Orion must travel along a route that meets the Moon where the Moon will be, not where it once was. Trajectory design therefore joins geometry with timing so closely that one cannot be separated from the other. As Artemis II moves outward, small correction opportunities remain part of the flight path. No practical mission depends on perfect initial placement alone. Tiny differences in performance, measurement, or environmental influence can shift the route slightly. For this reason, mid-course corrections exist as a discipline part of translunar travel. These are not admissions of failure, they are expected acts of refinement. A small engine burn at the right moment can move the future path by a meaningful amount. The earlier such corrections are made, the more economically they can shape what comes later. The translunar arc therefore includes not only initial departure, but also the possibility of measured adjustment. One of the most important features of Artemis II is that it is designed around a free return trajectory. Free return means a path that loops around the Moon and naturally returns toward Earth, even if no large propulsion action is taken after the lunar encounter. This idea gives the route a special character. It is not simply a one-way aim toward the Moon followed by an independent decision to come home. Rather, the path itself contains the outline of return within its geometry. The spacecraft departs Earth, falls outward along its planned curve, swings through the Moon's gravitational region, and then bends back toward Earth. Because of the way the overall route has been shaped from the beginning, this does not mean the flight is passive. Navigation, monitoring, and control remain constant. But the free return concept offers a fundamental safety advantage. It places the mission on a route that has resilience built into its large-scale design. The Moon's gravity does not merely serve as a destination marker, it acts as part of the turning architecture of the path. Orion approaches the Moon with substantial speed, enters the lunar sphere of stronger local influence, and experiences a gravitational redirection that alters the course back toward Earth. The motion resembles a great curve folded around the Moon rather than a stop at the Moon. Artemis II is a mission around the Moon, not a mission into lunar orbit or onto the surface. Because of this, the path must be understood as a continuous dynamic relation among three bodies. Earth remains the larger controlling mass for much of the journey. The Moon becomes increasingly important near encounter. The spacecraft responds to both according to the timing and energy of its route. The path is therefore a negotiated curve between gravitational influences rather than a simple transfer through emptiness. Even the Sun, though not the central actor in this specific corridor, remains part of the larger environment in which these motions occur. The translunar trajectory is exact because celestial motion is exact. It is demanding because the scale is great enough that small early differences become large later consequences. Seen in human terms, this path changes the meaning of distance. Earth recedes not through a sharp crossing of a border, but through continuous movement along the arc. The spacecraft grows farther from home hour by hour, yet the route itself remains mathematically intimate with Earth, since every moment of outward motion is still being shaped by Earth's gravity and by the return possibility built into the design. In this way, translunar flight is both departure and connection. Orion moves away, but it does so along a curve that never stops being defined by the world it has left. The route of Artemis II is therefore one of the most elegant realities of the mission. It is not only a way to get somewhere, it is the physical form of mission intent, the departure from Earth, the outward climb, the measured corrections, the close lunar passage, and the natural bending back toward Earth all belong to one coherent trajectory. The spacecraft does not wander between worlds. It follows a path written in gravity and timed in motion, a long, controlled arc that carries human beings through cislunar space and back by the quiet precision of celestial mechanics. As Orion approaches the Moon, the wide translunar arc narrows into a different region of space, one shaped by the presence of a smaller world that nevertheless exerts its own clear authority. Lunar near space is not broad cislunar distance in the general sense. It is the immediate neighbourhood of the Moon, where the spacecraft passes close enough for lunar gravity, lunar light, and the physical character of the Moon's surface to become the dominant surrounding facts. Here the mission comes nearest to its destination. The Moon is no longer a bright disk seen across great distance. It becomes a world with relief, shadow, texture, and measurable pull, filling more of the view as Orion moves through its sphere of influence. The Moon is much smaller than Earth, with a diameter of about 3,474 kilometers. Yet its mass is sufficient to govern the motions of nearby objects in an unmistakable way. As Orion enters this region, the balance of gravitational influence changes. Earth still matters, because the spacecraft remains within the larger Earth-Moon system, but the Moon now shapes the local curve of motion more strongly. This does not happen as a sudden crossing of an invisible wall. It is a gradual strengthening of lunar control as distance closes. The spacecraft's path bends in response. The Moon becomes not simply something to be seen, but something actively encountered through mechanics. Near the Moon, speed and gravity combine into a delicate relation. Orion approaches with the energy carried from its translunar flight, and the Moon pulls that moving spacecraft inward. The result is a fast passage, not a slow drifting arrival. Artemis II is planned as a lunar flyby rather than a capture into long-lasting lunar orbit. This means the spacecraft sweeps through the Moon's neighbourhood, comes to its closest approach, and then continues along a redirected path. The Moon acts like a turning influence in the mission, reshaping motion through gravity rather than receiving the spacecraft into permanent local residence. The appearance of the Moon changes steadily during this approach. From far away it is known mainly by phase, the familiar change in the sunlit fraction seen from Earth. At close range, phase remains real, but it is joined by much finer detail. The boundary between day and night on the lunar surface, often called the terminator, becomes especially revealing. Near this boundary, low-angle sunlight stretches shadows across crater walls, mountain slopes, and ridge lines, Relief stands out more strongly there than under high overhead light. Surface shapes that seem muted from a great distance become sharp and legible. The moon's face is written in shadow as much as in brightness. Its surface tells a very old story. Large dark plains, called Maria, spread across many familiar regions of the near side. These plains are ancient basaltic lava fields, the cooled remains of volcanic flooding that took place billions of years ago. Around and beyond them lie brighter highlands, heavily cratered and older still in exposed appearance. Craters of many sizes overlap one another, recording repeated impacts across immense spans of time. Some are simple bowls, others carry central peaks, terraces, or ejecta rays spread across the surface. From lunar near space, these forms are no longer abstract markings on a distant sphere. They become visible geology on a world without air, rain, or flowing water to erase them quickly. The absence of a substantial atmosphere is one of the moon's defining conditions. The moon has no thick envelope of air like Earth's. Instead, it possesses an extremely thin exosphere, so sparse that it does not behave like ordinary weather-bearing atmosphere at all. There are no clouds, no winds, and no blue sky over the surface. Sunlight falls directly. Shadows remain dark and hard-edged. The sky above the moon stays black even when the surface below is brightly illuminated. This gives lunar near space a special clarity. Nothing softens the contrast between light and darkness. The surface looks exposed, exact, and severe. Because there is no substantial atmosphere. Temperature at the surface depends strongly on sunlight and shadow. Areas in full sun can become very hot, while regions in long darkness can become intensely cold. The most extreme cold is found in some permanently shadowed areas near the poles, where sunlight barely reaches or does not reach at all. In the region of a flyby, Orion does not land or enter these shadows physically, yet the visual fact of strong thermal contrast belongs to the moon everywhere. Light on the lunar surface is not merely illumination. It is also the main divider between thermal states. The moon's gravity is weaker than Earth's, about 1/6 as strong at the surface. Even so, in near space it is quite capable of guiding trajectories, shaping low orbits, and altering the path of a spacecraft on a flyby. The moon is also not perfectly uniform in its internal mass distribution. Some regions contain concentrations of mass, often called mascons, associated mainly with large impact basins. These variations influence local gravity in subtle ways and matter especially for precise orbital analysis. The spacecraft passing through lunar near space moves within this slightly uneven gravitational field, though the large overall effect remains the moon's general pull and the bending of Orion's path around it. Dust belongs to the moon's nature as well, though from orbit or flyby it's understood more through the surface than through moving clouds. The lunar ground is covered in regolith, a layer of broken rock and fine powder created by countless impacts over vast time. Without air or liquid water, this material remains dry, sharp, and undisturbed except by impacts, slope failure, and rare electrostatic effects. It softens the appearance of some terrains while preserving the scars beneath. Seen from near space, the surface often looks both solid and powdery at once, a world of stone reduced over eons into a blanket of fractured debris. Another profound feature of lunar near space is the changing view of Earth. As Orion passes the moon, Earth no longer appears overhead in the ordinary human sense, nor does it dominate the field of vision as it does from low Earth orbit. Instead, it becomes a distant globe seen beyond the moon, bright with cloud, ocean, and land. Against the grey dryness of the lunar surface, Earth appears vivid and active. White weather systems swirl over blue water and darker continents. The contrast is striking not because Earth grows larger, but because the Moon reveals what Earth is by being so different. One world is airless, dry, and geologically quiet at the surface. The other is wrapped in air, shaped by water, and visibly alive with motion. In this region, the mission reaches its most intimate relation with the Moon. Orion does not touch the ground, but it passes close enough for the Moon to become more than an object of distance. Its gravity redirects the flight. Its ancient surface fills the view with cratered plains, highlands, and long shadows. Its lack of atmosphere defines the harsh clarity of the scene. Earth remains visible, but now as another world seen from near lunar space. Artemis II moves through this region briefly, yet the Moon's local reality is complete in that briefness, a silent, airless world whose presence is felt in motion, seen in stark light, and recorded in every marked and ancient surface below. After the Moon's near space, the mission narrows again from the outside world to the sealed world carried within Orion. Here the surrounding region is no longer open vacuum, strong sunlight, or lunar gravity. It is the cabin atmosphere, the small human environment enclosed inside the crew module. This inner world is limited in volume, carefully regulated, and entirely artificial in the plainest sense. It does not arise naturally from climate, weather, or landscape. It is made, maintained, and protected by engineering so that 4 human beings can live and work for days while moving far beyond the ordinary reach of Earth. In this region, the mission becomes most intimate. Survival depends not on distance crossed, but on the exact condition of air, pressure, temperature, moisture, and circulation within a closed shell. Air inside the cabin must first do what air on Earth does so easily that it is rarely noticed. It must contain enough oxygen for breathing and keep the total pressure within a safe range for the human body. Oxygen is the gas the body uses in metabolism, the quiet chemical process through which cells release energy from food. Yet oxygen alone is not enough. A cabin filled only with oxygen at ordinary pressure would create fire risk and other operational concerns. The atmosphere inside a spacecraft is therefore a managed mixture, shaped to support breathing while also preserving safety and system control. Nitrogen serves as an important companion gas in this balance, helping create a stable pressurized environment more like the conditions to which the crew is accustomed on Earth. Pressure matters because the human body is adapted to living under the weight of Earth's atmosphere. In open space, there is almost no outside pressure at all. The cabin must therefore provide inward protection by pressing outward from within. This pressure supports ordinary breathing, keeps body fluids in stable condition, and allows daily activity without the severe physiological danger that vacuum would bring. The cabin is thus not simply a room inside a spacecraft. It is a pressure vessel, a sealed volume whose atmosphere is held in place against the emptiness outside. Every hatch, window, seal, and connection belongs to this same requirement. Within that sealed atmosphere, circulation is essential. On Earth, warm air rises and cool air sinks because gravity allows convection, the movement of heat and air by buoyant flow. Inside a spacecraft in weightlessness, that familiar pattern weakens greatly. Exhaled carbon dioxide does not naturally fall away or disperse in the same manner it does on Earth. Warm pockets of air can linger. Moisture can remain suspended or collect in unexpected ways. For this reason, cabin fans and ventilation systems are not luxuries. They're fundamental parts of the habitat. They keep air moving so that oxygen is distributed evenly. Carbon dioxide does not build up locally, and temperature remains controlled across the cabin. Carbon dioxide removal is one of the most important hidden tasks within the cabin atmosphere. Every breath taken by the crew consumes oxygen and releases carbon dioxide. If allowed to accumulate, carbon dioxide can impair thinking, produce discomfort, and become dangerous. The spacecraft therefore uses systems that scrub this gas from the air. To scrub means to remove selectively through chemical or physical capture. In practical terms, cabin air is drawn through equipment that traps or absorbs carbon dioxide so that the atmosphere remains breathable. This quiet exchange, breath after breath, is one of the most continuous life-supporting processes inside Orion. Humidity also requires careful control. Each crew member adds moisture to the air through breathing, perspiration, and daily living. On Earth, moisture often disperses into large atmospheric space or condenses according to changing weather conditions. Inside a spacecraft cabin, there is no broad outside sky into which humidity can disappear. If water vapor rises too high, condensation can form on surfaces, equipment, and corners where temperature differs slightly from the surrounding air. Excess moisture can affect comfort, materials, electronics, and hygiene. The cabin atmosphere must therefore be dried to an appropriate level by systems that collect and manage water from the air as part of the spacecraft's environmental control. Temperature joins these concerns as another central condition of the cabin. Human beings function best within a relatively narrow thermal range. Electronics, displays, and onboard systems also have preferred conditions. The cabin cannot be allowed to drift from cold discomfort into overheating according to the spacecraft's outer exposure to sunlight or shadow. Interior temperature must be regulated with steadiness. This means heat generated by the crew, computers, lights, and other equipment has to be gathered, moved, and ultimately rejected through the spacecraft's broader thermal control system. Inside the cabin, the result should feel stable rather than dramatic. That stability is itself an achievement. It means the inner atmosphere remains calm while the outer environment changes between extremes. Odor, trace contaminants, and particulate matter also belong to this closed atmospheric world. A spacecraft cabin is small, sealed, and occupied continuously. Materials release tiny amounts of gases over time. Human presence adds further compounds through breathing, hygiene, food preparation, and routine activity. Dust or floating particles can also appear from clothing, packaging, and equipment use. Air filtration is therefore part of the cabin's quiet discipline. Filters help remove particles, and atmospheric monitoring helps confirm that trace compounds remain within acceptable limits. The crew does not simply breathe any air held inside the pressure vessel. They breathe air that is continuously circulated, cleaned, and checked. The sound of this environment differs from the silence outside. In open vacuum there is no ordinary sound transmission, but inside the cabin, fans, pumps, electronics, and airflow create a steady acoustic presence. The atmosphere that supports life also carries noise. This makes the cabin feel less like a sealed museum case and more like a working machine habitat. Air moving through ducts, equipment cycling on and off, and the constant low operation of environmental systems form the ordinary background of life inside Orion. The cabin atmosphere is therefore not still in the absolute sense. It is maintained through motion, circulation, and controlled exchange. Even smell and breath become signs of the cabin's closed nature. On Earth, A room is part of a vast planetary atmosphere. In Orion, the room is the atmosphere, or at least the entire portion directly available to the crew. Nothing can be taken for granted. A leak would matter immediately. A failed fan would alter circulation. A rise in carbon dioxide would change both comfort and safety. The enclosed air is therefore more than background. It is an active system, one that the crew inhabits while the spacecraft continuously sustains it. In this smallest inhabited region of the mission, Orion becomes a pocket of Earth-like condition carried through deep space. It offers breathable air, steady pressure, moderated temperature, managed humidity, and continual cleansing of the atmosphere, all within a limited volume bounded by metal, seals, and windows. The surrounding universe remains vast, airless, and indifferent. But inside the cabin a different order is preserved. It is not natural in origin, yet it supports natural human life. The cabin atmosphere is thus the most immediate environment of Artemis II, a carefully maintained envelope of habitability in which every breath depends on design, vigilance, and the uninterrupted work of the spacecraft itself. Inside the protected cabin and within its carefully managed air, the mission narrows further still, from the environment around the crew to the condition of the crew themselves. Deep space flight does not only move human beings through distance, it places their bodies and minds into a setting unlike the one in which human life evolved. Artemis II remains shorter than the longest stays in low Earth orbit, yet even a mission of limited duration beyond low Earth orbit brings real physiological and psychological demands. The body must adapt to weightlessness, confinement, altered day-night patterns, controlled air, limited privacy, and the constant knowledge of being far from Earth. The mind must remain steady within routine, alert within complexity, and calm within a small world surrounded by vacuum. One of the first bodily changes in weightlessness is the redistribution of fluids. On Earth, gravity draws blood and other fluids slightly downward, so the body lives in a continuous vertical relation. In weightlessness, that familiar pull is greatly reduced. Fluids shift upward toward the chest, neck, and head. This can create a feeling of facial fullness, nasal congestion, and a different sense of bodily balance. The face may appear slightly swollen. Legs may seem lighter or less full. These changes are not signs of illness in themselves. They are part of the body's adaptation to a condition in which up and down no longer structure circulation in the ordinary way. This fluid shift also affects how the body interprets orientation. Balance on Earth depends partly on the inner ear, which contains organs that sense motion, and the pull of gravity. In orbit or deep spaceflight, these signals change. The eyes may report one thing while the balance system reports another. The result can be space motion sickness, especially early in the mission. Nausea, dizziness, and disorientation may appear as the brain adjusts to a world in which floating replaces standing and turning, no longer matches lifelong expectations. Most astronauts adapt, but adaptation is not automatic in the first hours. It is a process in which the nervous system learns again how to understand movement. Muscles respond to weightlessness as well. On Earth, many muscles work constantly even during quiet standing, helping the body resist gravity and maintain posture. In a spacecraft cabin, that work is reduced. The large muscles of the legs, back, and trunk are especially affected because they are no longer required to support full body weight in the same way. Over time, if such unloading continued without countermeasures, muscles would weaken. Artemis II is not a months-long station mission, but the principle remains present. The body is built for use under gravity. Remove that load, and the pattern of effort changes at once. Bones are subject to a similar principle. Bone is living tissue, continuously renewed in response to stress and use. On Earth, walking, standing, and moving under gravity help maintain bone strength. In weightlessness, the skeleton bears less load, especially in the lower body. Over long missions, this can lead to measurable bone loss. On a shorter mission, such as Artemis II, the effect is limited compared with long-duration stays, yet the underlying biology does not disappear. The body begins responding to the altered mechanical environment from the start. Human spaceflight always involves some measure of adaptation away from ordinary terrestrial loading. Eyesight and spatial judgment can also feel different in a confined, weightless cabin. Without a normal floor beneath the feet and ceiling above the head, orientation becomes more flexible. A wall may serve as a working surface one moment and as a resting direction the next. Astronauts learn to move with efficiency in this changed geometry. But the mind must construct a new internal map of place. Small volumes can feel larger once movement is three-dimensional, yet they can also feel more crowded because every surface carries equipment, supplies, or another crew member in close reach. The body learns new habits of motion while the mind learns new habits of spatial understanding. Sleep belongs to this adaptation as one of the most delicate needs. Human sleep is shaped on Earth by darkness, light, routine, temperature, bodily posture, and the natural cycle of day and night. In spaceflight, many of these cues are altered. The cabin remains a controlled environment. Mission schedules define waking and rest times. The body does not lie down under its full own weight. Outside, views of Earth or space may not correspond to familiar daily rhythms. Good sleep, therefore, depends on discipline and preparation. Fatigue can dull attention, slow reasoning, and reduce emotional steadiness. For this reason, rest in space is not a luxury or an afterthought. It is a functional requirement for safe mission performance. Food and hydration also influence bodily condition. Appetite can change in space, especially during early adaptation. Congestion from fluid shift may affect taste and smell, yet eating and drinking remain essential to strength, alertness, and mood. The crew must maintain adequate intake even when the setting is unusual and daily routine is tightly structured. Hydration is particularly important because fluid balance, circulation, and general well-being all depend on it. The body in space still follows the same basic chemistry as on Earth, but the surrounding habits that support that chemistry must be maintained more consciously. The mind faces its own quieter demands. A mission such as Artemis II places a small group in prolonged close contact within a confined volume, under continuous operational purpose, far from ordinary social space. Privacy is limited, tasks are scheduled, communication with Earth exists, but distance gives it a different character from life on the ground. Emotional steadiness, therefore, becomes part of mission readiness. This steadiness does not mean the absence of feeling. It means the capacity to continue functioning with patience, clarity, and mutual respect under unusual conditions. Training supports this, but daily behavior sustains it. Attention is another central mental resource. Spacecraft operations involve procedures, checklists, timing, and the need to notice small deviations before they become larger problems. The mind must remain calm without becoming dull, alert without becoming strained. This balance is supported by routine. Routine in space is not mere repetition. It is a stabilizing frame that reduces unnecessary uncertainty. by giving structure to work, meals, exercise, maintenance, observation, and rest. Routine helps the crew preserve cognitive order in a setting where many natural earthly cues are absent. There is also the deeper psychological fact of distance. Beyond low Earth orbit, Earth is no longer the nearby world filling the sky beneath the station window. It becomes more evidently separate, a globe at real remove. For many astronauts, this can sharpen perception rather than disturb it. The mind holds together two truths at once. The spacecraft is small and enclosed, yet it moves within an immense setting. Earth is far, yet still visually present and emotionally central. This awareness can deepen concentration, humility, and the sense of collective purpose that a mission like Artemis II represents. In the body and mind of the crew, the inward journey of deep space becomes most real. Fluids shift, muscles unload, balance recalibrates, sleep requires care, and attention must be sustained within a small engineered world. At the same time, discipline, training, routine, and mutual steadiness allow human beings to function well in conditions for which the species was not originally made. Artemis II carries this quiet achievement within it. The mission is not only a movement of hardware through space, but a measured adaptation of living bodies and thinking minds to a realm beyond Earth. Within the small world of Orion, life does not proceed as a continuous stream of sensation alone. It is shaped into routine. The crew's daily work and ordinary habits give structure to time, and that structure becomes one of the quiet supports of the mission. In deep space, routine is not dull repetition. It is the method by which a small group keeps order inside confinement, protects attention, preserves health, and turns a limited cabin into a functioning human workplace. Every day contains checks, meals, cleaning, communication, observation, maintenance, preparation, and rest. Together these actions form the lived rhythm of Artemis II. The day begins not with sunrise in the ordinary earthly sense, but with a planned waking period. Time aboard Orion is organized by mission clocks and operational needs rather than by a natural horizon. The crew wakes according to schedule, not because morning light enters a bedroom window. This matters because the body and mind respond well to dependable timing. In a spacecraft, where external cues are reduced or irregular, the deliberate structure of the day becomes a substitute for the loose guidance that nature often provides on Earth. Waking, eating, working, and sleeping at defined periods help preserve clarity and steadiness. Soon after waking, the crew turns to personal care and the first checks of the day. These are simple acts in one sense and highly engineered acts in another. Washing, dressing, arranging loose items, and preparing food all take place in weightlessness, where nothing remains where it is left unless it is attached, stored, or held. A spoon does not rest quietly on a table. A packet does not stay flat on a counter. Water does not pour downward into a cup by gravity alone. The crew therefore performs small tasks with more deliberate hand control than would be needed on Earth. Ordinary life becomes a sequence of gentle captures, placements, openings, closures, and tethered use. Meals help mark the passage of the day. They also serve physical and social purposes at once. Food provides energy, hydration, and stability. But it also gives the crew moments of shared routine that break the mission into human intervals. Eating in Orion is practical rather than ceremonial. Packaged foods must be handled in a way that prevents crumbs, floating droplets, or lost contents from spreading through the cabin. Water used for drinking or for rehydrating food is dispensed carefully. The act of eating, therefore, carries both nourishment and discipline. Nothing is casual in the harmful sense. Yet the meal remains a familiar point in the day, one of the few elements of human life that still feels recognizable even in a radically altered setting. After these first personal and shared tasks, work fills most of the waking period. Artemis II is a test flight, so the crew's duties include evaluating Orion's systems under real mission conditions. They check displays, verify equipment behavior, monitor environmental systems, and compare actual spacecraft performance with expected results. This work is not a matter of watching passively while automation does everything important. The astronauts are active participants in confirming how Orion behaves with human beings aboard. They observe, record, respond, and at times take direct control during planned demonstrations. The day is therefore shaped by procedure. Checklists and timelines bring order to a setting where memory alone would not be enough. Manual operations add another layer to this work. Artemis II includes periods when the crew practices flying Orion directly, refining the skills needed for later missions that will demand rendezvous, proximity operations, and docking near the Moon. This means the astronauts are not only passengers carried by a highly automated spacecraft, they are trained operators using the spacecraft as a working vehicle. During such periods, attention narrows, hand controllers, displays, camera views, and motion cues all matter. The body may be floating in quiet weightlessness, but the mind is fully engaged in deliberate control. In this way, daily life aboard Orion includes moments of concentrated piloting within a broader pattern of system checks and mission duties. Communication with Earth is another steady part of the day. Some of this communication is technical, involving reports, status updates, or confirmation of procedures with mission control. Some of it is more human in tone, allowing the crew to share observations and maintain connection across distance. These exchanges help preserve a sense of continuity between spacecraft and ground. They also help organize the day. Talking with Earth is not only an emotional link, it is part of the operational rhythm of the mission, a means by which information, planning, and support move back and forth across cislunar space. Cleaning and housekeeping are quieter tasks, but they matter. In a small sealed cabin, disorder grows quickly if not checked. Items must be secured after use. Surfaces need attention. Waste must be handled properly. Clothing, equipment, food packaging, and personal objects all need places where they will not interfere with movement or systems. Housekeeping in weightlessness is not the same as housekeeping on Earth, but it serves the same principle. A cared-for environment supports clear thought and safe work. A neglected environment invites confusion, lost objects, and unnecessary strain. The crew therefore spends part of daily life simply keeping Orion livable. Movement itself becomes a practiced habit. There is no ordinary walking. The astronauts move by pushing lightly from one surface to another, guiding themselves with hands and feet through the cabin volume. Over time, this becomes efficient and graceful, but it always requires awareness of where other crew members, equipment, and stowed items are located. The cabin is both workplace and living space, so movement through it is a form of daily cooperation. One person preparing a meal, another checking a panel, and another accessing stowage all share the same small volume. Courtesy and choreography become nearly the same thing. Observation also belongs to the day. Orion's windows allow the crew to look outward at Earth, the Moon, and the surrounding dark of space. These views are not only emotional experiences, though they're certainly that as well. They are part of situational awareness, part of the human meaning of the mission, and at times part of planned activity. The crew makes visual observations, photographs, and records impressions of what they see. Looking outward thus becomes another layer of daily life, where operational awareness and reflective attention meet. At intervals, emergency procedures and unusual situations must also be rehearsed or reviewed. A test flight cannot rely on normal conditions alone. Part of the crew's work is to confirm that they can respond correctly if systems deviate, if timelines change, or if unexpected demands arise. This gives daily life a quality of readiness beneath its routine. Even during quieter hours, the mission remains an active test of people and spacecraft together. As the waking period closes, the routine narrows again into preparation for rest. Items are secured, tasks are completed or handed over to the next scheduled period, and the cabin shifts from active workplace to sleeping environment. The transition is important because it marks the boundary between effort and recovery. Even in space, the day needs an ending. The daily life of Artemis II is therefore built from small repeated acts that together sustain the whole mission. Waking, eating, checking systems, flying, cleaning, communicating, observing, and resting form a pattern strong enough to hold 4 people steady inside a small moving world. Routine becomes order. Order becomes confidence. And confidence helps turn deep space from an overwhelming setting into a place where human beings can live and work with calm purpose. At the end of the long curve through cis-lunar space, the mission narrows one last time into the final and most demanding passage of the crewed spacecraft itself. Orion returns toward Earth, carrying its crew inside the same protected cabin that has held them through launch, deep space flight, and the lunar flyby. Yet the spacecraft that comes home is no longer configured exactly as it was during the outward journey. Before entry into the atmosphere, the European service module separates. Its work belongs to space. It has provided power, propulsion support, thermal management, and essential supplies across the mission, but it does not remain with the crew for the last descent. What continues inward is the crew module alone, the blunt conical body shaped from the beginning for this return through air. This separation changes the meaning of the vehicle. In deep space, Orion is a joined system of forward shelter and rear support. Near Earth on return, that larger system is reduced to the single inhabited capsule. The crew module must now face the atmosphere with its heat shield forward and its protective geometry correctly aligned. Orientation is no longer a matter of convenient pointing for sunlight or communication. It becomes a matter of survival. The angle of entry must be carefully controlled. Too steep a path produces greater heating and deceleration. Too shallow a path risks a long skipping passage that can lead the spacecraft away from the intended descent corridor. Return is therefore not a simple fall. It is a guided encounter with Earth's atmosphere, requiring exact attitude and trajectory. As the capsule reaches the upper layers of air, the environment changes rapidly. For days, the crew has lived inside a spacecraft moving through vacuum, where heat enters or leaves mainly by radiation, and where no outside air presses against the hull. Now the crew module meets gas once again. At first, the atmosphere is extremely thin, but Orion arrives at such high speed that even these upper traces matter. Air in front of the capsule is compressed violently. This compression heats the gas to extraordinary temperatures, and a sheath of superheated plasma forms around the vehicle. Plasma is gas so energized that electrons are stripped from atoms, creating a state different from ordinary air. The glow surrounding the capsule during this phase is not flame in the familiar earthly sense. It is the visible effect of extreme heating in compressed atmospheric gas. The blunt shape of Orion now reveals its deepest purpose. A blunt body pushes the hottest shock layer outward from the main structure rather than drawing it tightly against a sharp nose. This helps reduce the heat transferred directly to the spacecraft. Even so, the thermal load remains immense. The heat shield at the base of the crew module begins doing the work for which it has been built. Its ablative material chars and recedes in a controlled way, carrying energy away while protecting the structure beneath. The capsule does not pass untouched through return. It survives by allowing its outer protective layer to change and partly sacrifice itself. Deceleration is as important as heating. As Orion drives deeper into thicker air, drag rises sharply. Drag is the resisting force produced by motion through a fluid. Here it is not merely an inconvenience. It is the very means by which the spacecraft sheds the enormous speed gained in space. The atmosphere becomes a braking medium. The crew, who've lived in weightlessness for the mission, now feel strong forces pressing them into their seats as velocity falls. Their bodies, adapted for days to free-floating movement, re-enter a world of acceleration and load. The change is physical and immediate. Earth reasserts itself through force as well as through sight. Communication can be affected during the hottest part of re-entry. The ionized gas around the spacecraft may interfere with radio signals for a period, creating a temporary communications blackout or degradation. This is a known feature of atmospheric return from high-speed flight. For the crew and ground teams, it marks one of the most isolated phases of the mission. Orion must continue through this interval by the soundness of its design, its guidance logic, and the stable behavior of the capsule in flight. The blackout does not define the return, but it sharpens its meaning. The spacecraft is now fully committed to atmospheric passage. As speed continues to fall, the plasma glow diminishes and aerodynamic control gives way step by step to the systems designed for the lower part of descent. The capsule remains a heavy body moving through air, but it is no longer a body in its most violent thermal phase. The next great transition is the deployment of parachutes. These do not appear all at once in their full form. The sequence is staged. Smaller drogues first help stabilize and slow the capsule. Then larger main parachutes open, spreading wide above Orion and increasing drag far more strongly. With these canopies carrying the load, the descent becomes slower and more measured. The crew module moves from fiery return toward controlled arrival. Below, the ocean waits as the final receiving surface. Artemis returns to splash down rather than to land on wheels or legs. Water provides a broad and forgiving recovery zone, though it also introduces its own demands of timing, flotation, and rapid response. The capsule strikes the sea with significant force even under parachutes, then settles into its floating posture. Motion changes again. The long arc through cislunar space ends not on a runway or a landing pad, but on moving water beneath open sky. Recovery begins quickly. Teams approach the capsule, assess its condition, secure it, and begin the process of bringing crew and spacecraft into safe post-flight handling. Fresh air, sea state, wave motion, and ordinary gravity all return together. For the astronauts, this is a profound bodily change. After days in a controlled cabin and in weightlessness, the senses meet wind, motion of water, natural light through Earth's atmosphere, and the full downward pull of gravity. What had been distant throughout the mission now surrounds them again in direct physical form. The meaning of this return is larger than the single descent. Artemis II is the first crewed mission of the Artemis program to travel around the Moon, and its closing passage through Earth's atmosphere marks the completion of more than a technical demonstration. It confirms that Orion can carry human beings out through cislunar space, sustain them around the Moon, and bring them safely home through the hardest thermal and mechanical phase of the journey. The mission closes as all successful exploration flights must close, not only by reaching distance, but by returning from it with knowledge made real in hardware, procedure, and lived human experience. In the end, the return through fire gathers the entire mission into one final act. The service module falls away. The crew module turns its shield toward Earth. Plasma surrounds it. Drag takes hold. Parachutes open. Ocean receives it. Recovery completes it. What began on the coast of Florida as a departure into vast space ends in water under Earth's sky, with a small scorched capsule holding the proof that human beings can once again travel around the Moon and come home. Now the motion grows quieter in the mind. The heat of return has passed. The sea has received the capsule, Earth, which once stood below as a distant globe beyond the Moon, has become the full surrounding world again. Air moves. Water shifts. Gravity settles back into the body with its old familiar weight. The spacecraft that crossed the wide region between worlds has become still enough to be touched by human hands from outside. Metal, seals, scorched surfaces, and cooling structures rest after their long work. Above, the sky returns to its earthly colour. It is no longer the black depth seen through windows in cislunar space. It is softened by air, brightened by scattered light, and shaped by the same atmosphere that first resisted ascent. The mission has moved outward through vacuum and silence, around the Moon's ancient face, and back through heat into weather and sea. Yet the deeper movement has been one of continuity. Earth remains Earth. The Moon remains the quiet companion world. Between them, human craft has passed once more. Inside that completed passage there is no need for haste now. Systems can fall silent one by one. Checklists can end. Voices can lower. The body can rest under the downward pull it has known since birth. Breath belongs again to a planet-sized atmosphere rather than to a measured cabin. The mind no longer has to hold trajectory, procedure, and enclosed routine with such steady care. It can widen and become calm, far above. The Earth-Moon region remains as it was immense, ordered, dark, and full of motion without sound. The path of Artemis II has briefly crossed it, leaving no mark in the vacuum, only knowledge carried home. The great curve around the Moon is complete. The small human world inside Orion has endured it. Night can now gather gently over sea, shore, and sky. While the memory of that quiet journey drifts into stillness,